In this video, I will be discussing about the fundamental theorem of calculus. This fundamental theorem of calculus is an extremely powerful theorem that establishes the relationship between differentiation and integration and gives us a way to evaluate definite integrals or calculating areas without using Riemann sums. Actually, the theorem consists of two parts. So at this time, I will be discussing the first part. So this is now the first part of the fundamental theorem of calculus. If the function f of x is continuous over a closed interval a to b, and the function big F is defined by this integral, the integral of f of t dt from a to x, then for every x in the interval, the derivative of this integral is the small f of x. That is, the derivative of the big F of x is the small f over a closed interval ab. Now in this theorem, let us discuss first some of the subtleties in this theorem. Now you see here that this integral is a little bit different from the indefinite integral that we have discussed in the previous video, because we see here some expressions that we have not seen before, this a and this x. Now we call this a as the lower limit of this integration and x as the upper limit of this integration. So a and x here are called the limits of integration. And this small f of t is what we call the integrand function. And this dt is the index of integration, which gives us the idea that the integration is done with respect to t. Now, I would like to invite you to see that there are two parts in this theorem. This hypothesis part of this theorem and this conclusion part of the theorem. Now, the hypothesis part of the theorem states that the big F of x is the antiderivative of small f of t over a closed interval a to b. Now in the conclusion, it states that for every x in the interval, the derivative of this big F of x, which is this one here, is the small f of x. That is saying that when you get the derivative of this integral, the result is the function inside this integration notation, which is the small f. So we say here that the derivative of the big F of x is the small f. And this theorem establishes the relationship that differentiation and integration are inverses to one another. These are inverse operations to each other, because the derivative of the integral of the f is the f itself. Now, in a drawing, we see here that suppose this is the t-axis and this is our small f axis, then the small f function is this one. So this is our y, which is equal to small f of t here. And according to this theorem, that this function f is continuous over an interval from a to b. So if you get the area from a to b, and suppose we pick an element in this interval, say this is our x here, at this point here, the area below this function is our big F of x. So this is now our big F of x here. And if you are going to pick a little bit to the right of this x, say this one here, at this point. So there is an increase of h. So this point is x plus h. So there is an increase in the area by this part here. So to write the proof for this theorem, we will use the definition of our derivative, which we've learned from our Calculus 1, which says that the derivative of our big F of x is defined to be the limit of our big F of x plus h minus our big F of x divided by h, where h is approaching 0 here. So this is now our difference quotient definition of derivative. However, we can factor out this h here in this fraction. So we have the derivative of the big F of x is equal to the limit of 1 over h times this difference here. And we know that our big F in the definition of this theorem is defined to be the integral of our small f function. So instead of writing this one, we will write the integral from a to x plus h of our function small f of t dt. And this is subtracted by the integral from a to x of our f of t dt here. Why? Because our big F of x is defined here in our hypothesis of the function, that the big F is defined to be the integral of our small f. But since our independent variable here is x plus h, so this integral here is the area from a to this one here, x plus h. So this is now our integral from a to x plus h of our function f of t dt here. But this second integral is the area from a to x here, this one here. So this is our integral from a to x of our function small f of t dt. Now, suppose we will reverse these limits of integration. This lower limit will become the upper limit, and this upper limit will become the lower limit. We will be writing a negative in front of this integral. So we have the derivative of the big F of x is equal to the limit of 1 over h of the difference of the integral from a to x plus h of our function small f of t dt minus of the negative 1 of the integral from x to a of our function small f of t dt. Why? Because we reverse the order of our limits from x to a here. So rewriting further, this is the derivative of the big F of x is equal to the limit of 1 over h of the integral from a to x plus h of our function small f of t dt plus the integral from x to a of our function small f of t dt here. Now remember that our h here is moving to 0. But we notice that this one is an average value of the small f of t here. Now we see that this integral is the area from a to x plus h. And this integral is just the area from x to a, which is this one here. Now, the sum of this times 1 over h is just an average value of the function small f over the interval from x to x plus h. So we write here that the derivative of our big F of x is equal to the limit of 1 over h times the integral from x to x plus h of our function small f of t dt here as h approaches 0. Why? Because we see this one that this is just an average value of the function small f over this interval from x to x plus h. So this little interval here. Then we say that by the mean value theorem for integrals, there is some number c in this interval from x to x plus h. So this interval which is here, so I can find some number here which is a number c such that 1 over h times the integral of x to x plus h of our function f of t dt is equal to the small f of c. And since c is a number in this little interval x to x plus h, then this number c is approaching to x as h approaches to 0. And since f of x is continuous, the limit of our f of c as h approaches to 0 is equal to the limit of f of c as c approaches to x. And the limit of this function is just f of x. Thus, substituting this one to our previous equation, we have the derivative of our big F of x, which is equal to the limit of this 1 over h of this integral. We will write the limit of f of c here as h approaches to 0. Why? Because we have this one here, that 1 over h times the integral of our small f of t dt is small f of c by the mean value theorem. And this limit f of c is just f of x here in this statement. So we say that our derivative is just equal to the limit of f of c, where c is approaching x, because c is approaching x as h approaches 0. So geometrically, when your h is getting smaller and smaller, your c will be approaching closer to x. That is the notion about squeeze theorem. So this c here, which is in between x and x plus h, when this increment of h becomes smaller and smaller, there is no way that c will go any further, but it moves closer to x here. So therefore, our derivative of big F of x is equal to the small f of x. And that is the end of our proof, which establishes the relationship of antidifferentiation and differentiation. That if you find the derivative of the antiderivative, it goes back to the original function small f of x. So at this time, let us apply to some examples here. So what is the derivative of the integral of the function the square root of t squared plus 7 from 0 to x dt? So here, to find the derivative with respect to x of this integral of the square root of t squared plus 7 from 0 to x dt, we write that this is the derivative of our integral from 0 to x of our function small f of t dt here, where our function small f of t is equal to the square root of t squared plus 7. Now, using the hypothesis of the fundamental theorem of calculus, which is this one here, our integral is our big F of x. So instead of writing that integral, I will write big F of t. And this big F of t is evaluated from 0 to x. So evaluating this one from 0 to x is big F of x minus big F of 0. So we just evaluate this big F by these limits here. And we know that the derivative of the difference is the difference of their individual derivatives. So we have the derivative of our big F is big F prime of x, and the derivative of this one is big F prime of 0. And we know from the conclusion of the fundamental theorem of calculus that the derivative of the big F of x is the small f of x. So here, this is equal to the small f of x, and the derivative of this, because this is a constant, the result is a constant, and the derivative is 0 here. So therefore, our small f is the square root of t squared plus 7. So this is the square root of t squared plus 7, but our t here is x. So this is x squared plus 7. So this is now our answer if we want to find the derivative of the integral of this square root of t squared plus 7. So as you can see in our answer, as if the differentiation of the integration cancels each other, and this t will be replaced by x. Now let's proceed to example number 2. So what is the derivative of this integral of e to the power square root of t from 0 to x to the power of 5 dt? So to solve this one, we write here the derivative with respect to x of the integral from 0 to x to the power of 5 of e to the power the square root of t dt. We write this one as the derivative with respect to x of the integral from 0 to x to the power of 5 of our f of t dt, where our small f of t is this function here, which is e to the power of the square root of t. And we know from the hypothesis of our fundamental theorem of calculus that this integral of the small f is our big F of x. So this is the derivative of the big F of t evaluated from 0 to x to the power of 5. So evaluating this one from the limits from 0 to x to the power of 5, we have the big F of x to the power of 5 minus the big F of 0 here. And we know that the derivative of a difference is the difference of their individual derivatives. So the derivative of this big F of x to the power of 5 is big F prime of x to the power of 5. And the derivative of this is the big F prime of 0. And what is the derivative of this big F? The derivative is the small f using the fundamental theorem of calculus. So this is the small f of x to the power of 5 times the derivative of our x to the power of 5, which is 5x to the fourth. Why? Because this is using the chain rule. So the derivative of our outer function big F is the small f, but using the chain rule, we need also to find the derivative of our inside function, which is x to the power of 5. That's why we have 5x to the power of 4. And the derivative of this big F of 0 is 0, because this is just a constant. So here, this 5x to the power of 4 will be multiplied by our small f. And our small f is here, e to the power, the square root of t. But our t here is x to the power of 5. And this is our final answer here. So, looking at our given, as if we just cancel the differentiation and the integration and copy this function here after substituting your x to the power of 5 to your t. But we need to multiply this one by the derivative of x to the power of 5, which is 5x to the fourth. Now let's proceed to our example number 3. What is the derivative of the integral of the square root of t squared minus 8 from 5 to x cubed dt? So to solve this one, we write here as the derivative with respect to x of the integral from 5 to x cubed of the function the square root of t squared minus 8 dt. But this one is just the derivative of the integral from 5 to x cubed of our function small f of t dt. So instead of writing the function, we'll just write this one as our small f of t. So we write here where our small f of t is equal to the square root of t squared minus 8. So using the hypothesis of our fundamental theorem of calculus, the integral of the small f is the big F of t, evaluated from 5 to x cubed. And evaluating this one from the limits of our integration, we have big F of x cubed minus the big F of 5. And we know that the derivative of a difference is a difference of their individual derivatives. So this is big F prime of x cubed minus the big F prime of 5. And from the conclusion of the fundamental theorem of calculus, that the derivative of the big F is the small f. So this is small f of x cubed. And using the chain rule, we need also to find the derivative of x cubed, which is 3x squared. And we know that the derivative of a constant is 0, because when 5 is substituted to the derivative function, the result is a constant. And we know that the derivative of a constant is 0. So here, our small f, we know that this is the square root of t squared minus 8. So this is the square root of t, and our t is x cubed raised to the power of 2, because this is t squared minus 8. here times the 3x squared. So finally, our answer is 3x squared times the square root of x to the power 6 minus 8. And this is our final answer here. Now looking at our given, it is just this integrand here, substituting your upper limit here. But don't forget to multiply to the derivative of x cubed, which is 3x squared. So here in our example 4, to find the derivative with respect to x of the integral from x cubed to x to the power of 5 of the square root of t to the power 4 plus 5 dt, we write here that this is the derivative with respect to x of the integral from x cubed to x to the power of 5 of our function small f of t dt. So instead of writing this function, we just write small f. So we will write here that our small f of t is just equal to the square root of t to the power of 4 plus 5. So using the hypothesis of the fundamental theorem of calculus, that this integral of the small f is just the big F. So this is the big F of t evaluated from x cubed to x to the power of 5. So evaluating from the limits of integration, we have the big F of x to the power of 5 minus big F of x cubed here. And we know that the derivative of a difference is just the difference of their individual derivatives. So this is big F prime of x to the power of 5 minus big F prime of x to the power of 3. Then using the conclusion of the fundamental theorem of calculus, that the derivative of the big F of x to the power of 5 is the small f of x to the power of 5. And using the chain rule, we need also to multiply to the derivative of x to the power of 5, which is 5x to the power of 4. And this is subtracted by the small f of x cubed, because the derivative of the big F is the small f, times the derivative of x cubed, which is 3x squared. And we know that our small f is this function here. So this is equal to the square root of our t, and our t is x to the power of 5, but we need to raise this one to the exponent of 4 plus 5 times the derivative, which is the 5x to the power of 4, the derivative of our inside function x to the power of 5, minus the square root of x cubed raised to the exponent of 4, and this is added to 5 times the whole thing by the derivative of our inside function, which is x cubed, and the derivative is 3x squared. So we have 5x to the power of 4 times the square root of x to the power of 20 plus 5 minus 3x squared times the square root of x to the power of 12 plus 5. And this is our answer for this example number 4. Now let's proceed to our example number 5. Find the derivative of our big F of x if our big F of x is defined to be the integral from x to 2x of t cubed dt. So to find the derivative of the big F of x, this is just the derivative with respect to x of the integral from x to 2x of the function t cubed dt. And instead of writing t cubed, I will write just small f of t dt. So we need to write here that our small f of t is just t cubed. Now, at this time, let us apply the property of the integrals that we can split these limits here. So we have d by dx of the integral from x to 0 of f of t dt plus the integral from 0 to 2x of f of t dt here. So we'll see if we come up the same answer if we will not split these limits of integration, because instead of having limits from x to 2x, you will have from x to 0 added to the integral from 0 to 2x. So from x to 0 and then from 0 to 2x, that is x to 2x. And reversing these two limits here so that our variable should be at the upper limit and the constant is at the lower limit, we have the derivative with respect to x of the integral from 0 to x, but since we reverse the order, we place a negative sign in front of the integral symbol. So this is added to the integral from 0 to 2x of the small f of t dt here. So using the hypothesis of the fundamental theorem of calculus that the integral of the small f is the big F of x. So this is the derivative with respect to x of our big F of t, but this is negative here, evaluated from 0 to x, plus the big F of t here, evaluated from 0 to 2x. But remember, we need to get the derivative of this sum. And we know that the derivative of a sum is the sum of their individual derivatives. So we write here the derivative with respect to x of our negative big F of t evaluated from 0 to x, plus the derivative with respect to x of our big F of t evaluated from 0 to 2x. Then, using the grand statement of our fundamental theorem of calculus that the derivative of the big F is the small f, and evaluating this big F function from the limits of integration, we have the d by dx, so we just factor out the negative here, of the big F of x minus the big F of 0 here. And this is added to the derivative of the big F of 2x minus the big F of 0 here. Then, using the fundamental theorem of calculus that the derivative of the big F is the small f. So this is the small f of x minus 0, because big F of 0 is a constant and the derivative of a constant is 0. And this is added to the small f of 2x, because again, the derivative of the big F is the small f using the fundamental theorem of calculus. But we need also to multiply this one by the derivative of 2x, which is 2. And maybe you ask a question, why we were not able to multiply by the derivative of x? The derivative of x, we know it's 1. So f of x times 1 is just f of x. But here, this is a constant and the derivative of a constant is 0. So we have our answer as the negative of our f of x, and our f is t cubed. So this is x cubed here, plus this 2x, this is 2x quantity cube, because our small f is t cubed. But this is multiplied by its derivative of 2x, which is 2. So we have negative x cubed plus 8x cubed times 2. But 8 times 2 is 16 here. So this is 16x cubed minus x cubed. So therefore our answer is 15x cubed. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.